Okay. So I have practice problems for Euler paths and circuits. Let's get started. Okay, so each graph, which we have 12, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 to work on. Each of them, we're going to find the degree for every vertex, determine whether each graph contains an Euler circuit or Euler path or neither. This one is degree 3. Okay, degree 3. So if we get one more odd vertice or vertex, it will not have an Euler path or Euler circuit. And that is a degree 3. So I can go ahead and stop right there if I want to. I mean, it's kind of quick to just label the rest of them. So 3, 2, 2. And I can post this problem page to the module for this week if you want to practice after class. Okay, so there are more than 2 odd vertices. Let's do like these ones. So we have to go with neither. Okay, next graph, we're just moving to the right. So it's a connected graph, and we're just checking the degree of every vertex. Start here. It's even, so degree 2. And then degree 4. Degree 2. And 3. There's 2. The last one's going to be 3. Oops. Since there are 2 odd vertices, we have an Euler path somewhere in this graph. We don't have to actually find it, but we can just state that there is one. Okay, number 3. This one has degree 2. Let's move over here. So degree 1, 2, 3, 4. So degree 2. There's degree 3. And so let's see what this is. Degree 1, 2, 3, 3. So it's the same kind of situation. There are 2 odd vertices, which means I could find an Euler path in this graph. Okay. Moving along. So we've got neither, Euler path, Euler path. Let's try. Right here. Degree 1, degree 2. Degree 1, 2, 3. This is degree 2, and the last one's degree 2. Oh, okay, I see. I see the odd ones. This one, oh, trying to get color. And this one. So another Euler path could be found in this graph. Select the color first. Oh. One moment. Hey everyone, sorry about that. Okay, cool. Back to sharing. Okay. We're just trying to write that we found an Euler path and then got lost from screen share. So the next graph is this interesting triangle, and we're going to just check all of the degrees of the vertices. So starting with the top, degree 3. Let's go down to the bottom left, degree 3. And another 3. And 1, 2, 3. So these ones are all odd. So for Euler's circuit, you need no odds. This is where you have a situation of more than 2 odd vertices, so we have to go with neither. Okay. Just checking out all of these graphs. So here we've got degree 2. And 2. This is degree 3. Let's check this out. 1, 2, 3, 4, 5, 6. Double check that one. Starting here. 1, 2, 3, 4, 5, 6. Twice. 3 times. 4 times. 5 times. And the 6th time. Cool. Okay, degree 2. And 2. And 3. All right, then I have 2 odd vertices, which means there's going to be an Euler path. Okay, next group of graphs is right here. On the left side, let's go through the degree of every vertex, see what happens. Here's a 2. And 2. That's going to be degree 2. This is a 2. Let's stay with these easy ones. There's 2. And 2 on the other quarter. Cool. And then this is 1, 2, 3, 4. Sweet. Okay, I'm going to try making sure I don't mess this one up. 1, 2, 3, 4, 5, 6. Cool. These are all even. First time. Oops. And when it's all even degrees, we can find an Euler circuit, which means it has an Euler path and an Euler circuit, but Euler circuit is stronger. So we're going to say all even. Okay. Euler circuit. Oh, I like square. Okay, moving over, checking the degrees of the vertices. So I'm going to go for these kind of easier ones where I can tell that this is degree 2. And then the next one down is a degree 2. Right about there. Cool. Let's go over here. Degree 2. This one's a degree 2. Closer. Degree 4. 1, 2, 3, 4. Okay, let's use some color or something. This is 1, 2, 3, 4, and the other side I think is also going to be 4. Oh, same thing. Okay. Yeah. There we go. Okay, 1, 2, 3, 4. All even. Nice. So this is another Euler circuit. When you have all even vertices, you can not only find an Euler circuit, but also an Euler path. Well, we're just going to label Euler circuit, which is the best definition. Okay, this square over here on the right is a graph where we're checking every degree of every vertex. Degree 2. Degree 1, 2, 3, 4. This is degree 2. Degree 1, 2, 3, 4, 5. Okay. Degree 2 and oops. This is 1, 2, 3, 4 on the side. Degree 2. This is degree 1, 2, 3, 4 in the middle. There. And degree 3. Okay, so I have two odds, the 5 and the 3. Oops. Okay. Let's get that. Euler path. It's not as strong as an Euler circuit, but it's still a path where you don't repeat any of your edges. Or it's a sequence of connected vertices where you don't repeat an edge. Okay, last examples. Just checking the degree of every vertex. So degree 2. And 2. And this is a 2. And 2. Here's 2. 2. 1, 2, 3, 4. Cool. 1, 2, 3, 4. Again. 2. 2. Just going across here now. And 2. Okay, so if I've got a lot of evens, so let's keep on going. This is degree 1, 2, 3, 4. Let's put it inside. Cool. And 1, 2, 3, 4. Cool. Let's see. We've gone here, here, here. All through there, moving to here. 1, 2, 3, 4. Degree 1, 2, 3, 4. This one is degree 4. So 1, 2, 3, 4. And another 4. And a 2 and a 2. So I've got all evens, which is cool. I've got an Euler circuit somewhere in this graph. So just a reminder, an Euler circuit is a sequence of connected vertices where you don't reuse any edges, you start where you end, and you visit every edge. Okay, last one. So degree 2. Oh, no. This is a 3 and a 3. So I could go ahead and stop here. Well, actually, let's continue. If there's another odd, then I'll stop. That's a 2. Okay, here's a degree 3. So I can see that there's more than 2 odd vertices in this graph, which means that I can't find an Euler path or Euler circuit. So this is neither. Okay, so I will just go ahead and save this. I'll post all of the work we've done to today's module, to this week's module. I have another worksheet to do, but I just want to go back to the board and do the definition for Euler circuit and Euler path. I know we've done it before, but it's good to just write things down. Helps us learn. Okay, so let's even back up further to just plain walk path circuit. So sequence of vertices, one's connected to the other by an edge. In a path, you can't reuse an edge. You can reuse a vertex, but can't reuse an edge. And also just a reminder, the vertices are the dots and the edges are the lines or the connections. Okay, circuit. It's a sequence, so each vertex is connected to the next by an edge. It's also a path. You don't reuse edges. And the start is the same as the end. So even if it starts where it ends, you also have to check that you don't reuse edges. Okay, today we've been working on Euler path. Which is a path. You don't reuse an edge. Don't reuse edges. But you also use all of the edges. And then the Euler circuit is a path and a circuit and an Euler path, and the start is the same as the end. Don't reuse edges, starts the same as the end, and use all of the edges. I'm sort of thinking to go to that worksheet and pick one of the graphs that has an Euler path and find an actual path, and an Euler circuit and find an actual circuit, and then go back to just the abstract idea of knowing that there just is one somewhere. Okay, so I'm just going to pick one of those graphs. I'm going to pick the one that looks like this. Comes down, 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 over. Okay, we did this graph and found it has an Euler path. And we're going to find one. So I can remember we want to start at one of the odd vertices. Let me think about it. This is a Well, we'll just give it a try. Let's start at one of the odds. Let's just start at the top. Let's go from 1 to 2, or just straight down to the next vertex. To the vertex U is degree 3. Let's go down to one with degree 2. Over to this side. And then I can go here. All right. Let's label. It'll help. A, B, C, D, E. Okay, so I did find another path. It goes from A to B to C to D, E, and back to C. So I went from each vertex to the next using an edge. I used every edge one time, and I used all of the edges. Okay, now I'm going to pick one where we found an Euler circuit. Cool, this one looks kind of easy to draw. Let's draw this kind of square graph. The one that goes from here over, down, middle. And then it had a connection. And another vertex here. Okay. I'm going to pick anywhere, and also some labels will help us. Just do QR, S, T, U, B, W, X. Okay. Let's pick just this corner here. Let's start at S. So if it's going to be an Euler circuit, we can cover every edge, visit all of the edges, and start where we end. So if we start at S, we can end at S. Let's give it a try. Okay, let's go from S to T. And then from T, we'll go, just go over to U. From U up to V. V, let's go back down to T. So again, you can revisit a vertex. You just can't go over the same edge more than once if it's going to be an Euler circuit. let's go from T over to R. Uh-oh. I think I have a problem. Okay. So if I go to R.
No, because you can go from V to T to then R to then X to then V to then W to then R to then S.
Oh, you're right.
So
yes.
yeah, you would be fine, I think.
I think we can do this. Yeah. Thank you. Awesome. It's like, yeesh. I seem stuck, but we're not stuck. So we're going to go to R. Wait, hang on. Nope, that was it. S. T. To U. To V. To T. We want to go to R. And we're going to go, I think, this way and then back. Cool. This is okay. As long as I just go, let's go to X and then to V. And we can go through here. We got to go V to W, W to R, and then we can go back to down there and reach S. All right, so we got to V. V is going to be going over to W. W to R. And then we can go R to S, and we've made it back to the beginning. Okay, so Euler circuit. You start where you end. You started at S and ended at S. Okay. Almost had trouble, but thank you for the help to find a way to cover every edge just one time. So that part, use an edge once is being a path, and just a path. Using all of the edges makes it an Euler path. And if you use each path once, use all the edges, and start where you end, it's even better. It's an Euler circuit. Okay, so I have a way to apply these ideas. Right now, it's just a problem similar to your homework problem, but next week I have one or two kind of different ideas that are like ready for your review. Okay, so just checking out this first graph. And it is a map of a neighborhood laid out like a grid. And we want to see if a mail carrier can walk down every street only once and return to the place where they started. So we're looking to have the start the same as the end. Let's see if I can do this. Ending where you start means we want a circuit. And also visiting each street one time. Every street part means it's an Euler circuit, and using each street once is a requirement from needing to be a path and then a circuit. So we need all three together to get an Euler circuit. Okay, so this is what we want, but we have to see if it actually exists. So this is just kind of thoughts to the side. So let's do the work. This one is degree 3. This is degree 4. And then degree 2 is on that corner. Okay, degree 4. Let's just move here. This is degree 3. So actually I could have already stopped. As soon as I found an odd vertex, I cannot have an Euler circuit. An Euler circuit needs all evens. Let's see. Okay, something like that. Forget how I put your options in the homework, but you're checking if the degree of every vertex is even. It's not. So it does not have an Euler circuit. All right, I have another graph, so another map of a neighborhood where we're looking to find an Euler circuit. So let's see what we get. This is degree 2. And 2. 1, 2, 3, 4 is the next. And a 2. Okay. 1, 2, 3, 4. 2. 2. 1, 2, 3, 4. Oops, wrong tool. This looks confusing. Back to degree 1, 2, 3, 4. Got this. Inside here is 1, 2, 3, 4. And let's go down to 1, 2, 3, 4. And 4. Okay, so I'm just going to make sure I got all of the vertices, but so far it looks like everything's even, which means we would be good to go. Let's check though. This one's even. Got it, got it. Even. Cool. So they are all even, so I can find an Euler circuit. So I can start somewhere, cover every street, and end up where I started, and only go down each street one time. So just looking back at the two maps, in this map, we didn't have all even vertices, so we can't start somewhere, cover every street one time, and then end at the same spot. The other one we can. The other one has all even vertices, so I can start somewhere on this graph, go down each street one time, make sure I visit all of the streets, and get back to where I started. So I'll save this and post this one to this week's module as well. Let's see, do you have any questions or concerns? Because we've kind of finished the graph theory material, but if you want to go back over anything, we have time. Okay, so I will try to put together sort of a short list of topics to study or study guide and just present. We won't have time to type it, but we'll present that next week. And then we'll do practice problems next week for your last test. Okay, have a good weekend, everybody. I'll see you